this. Have we already covered that? Does that look familiar to anybody?
No.
Okay, good. Then we are on schedule. All right. Yeah, I was really concerned about that. Like, have I already talked about it? Because I have in at least 2 other and maybe 3 other classes. It all can get mixed up. Also, I need to reorganize our calendar around Monday and Wednesday because I thought I was spreading things out, but actually I'm just confusing myself now, so you might be confused also. So that's one of my goals over the weekend, is make all of the due dates either on the Monday of the week or the Wednesday of the week. And what that means for you is nothing new really. What that means for us is that we can just be clear on what's going to be covered on what day. Okay, you can still do it after that day. Ignore the little signs that say past due. All right, well, let's talk about piecewise defined functions. They're
Don't
different.
forget to set record.
Ah, thank you, I already have. Ha. But I appreciate it, always remind me. Okay, so these are actually used in real life by shipping companies. When you go to ship something, if it's a certain weight, you pay so much. And there's a range of weights that you still pay the same price. But then once it weighs above a certain point, you go to a different price range. Well, that's what this is. That's what piecewise defined functions are. And I'm sure business has their own name for it, like step function, but we call it in math piecewise defined functions. So that's what we're talking about today. So I'm going to make the picture bigger. Oh, heck, I'm going to go back and make sure I really am. I'm always insecure about this. Yes, I am recording. So. There now, make it bigger. Make sure everybody can see. Okay, this is a piecewise defined function. I am going to put this document to bed. This is already in your folder, your module. Instead, what I'm going to do is I'm going to get it from here. Maybe. Yeah. Okay. There we go. All right, this g of x is a piecewise defined function. Okay, this is, I think, number 2 number 2 in your homework. Notice that most functions are written as f of x equals, I don't know, I'm just going to make something up, 3x plus 2. Most functions are written like this. And then you go and you do whatever you're supposed to do with them. You evaluate them, you graph them, you do whatever you're going to do. These are a little more complicated. For instance, notice, now that's a little too big because the print looks strange. So I am going to, how about 110, 115. Yeah, I think that's good. I just want to make sure you can see. Yeah, okay. Notice what this says. It says this function right here, g of x, equals two different things. So we're going to talk about what that says. This is really a discussion of domain and what's going on in different parts of the domain of the function. And it ends up that for this function g of x, you've got two different things going on depending on where the x's are on the x-axis. So what we have here, if you pretend this is the x-axis, let me write an x. Let me write an x. And of course your positive infinity is way out there, and your negative infinity is way out there, and this is our x-axis, and that's a function. And here's 0 on the x-axis, which means you've got the y-axis going up here like this, and down here like this. But we're not really looking at that right now. We're just looking at the x-axis. And how, according to this, that this change from this function to this function, or I should say subfunction, right? Because they're both parts of one function, which is g of x. But if you want to call it that, this subfunction is dominant when x is to the left of 2 or equals 2. Now, if x is to the right of 2, this one takes over. And they're actually separate graphs if you were graphing them. But all you're having to do in the first problems in this set is to evaluate them. So notice we're looking for g of -8, g of 2, and g of 8. And remember that the numbers in the parentheses are always x's. And where do x's live? They live on the x-axis. So what I'm going to do is I'm going to locate those points. Here's -8 on the x-axis. Here's 2 on the x-axis, a very important point, because that's where the change from this function to this function takes place. And then here's where +8 is. And yeah, we are asked about g of 2. And that can be the biggest problem. What happens at 2 when 2, x equals 2, is where this change occurs. So, what we have to try to figure out is, where is x plus 9 going to happen? Where is 8 minus x going to happen? X plus 9 lives over here. And I'm going to like draw a dashed line up here just to separate. This is the area of the graph, up and down really. To the left of x equals 2, and this is the part to the right of x equals 2. And to the left of x equals 2, g of x actually equals x plus 9. So if you're evaluating, that is taking a number from the x-axis and putting it into g of x, you're going to be using this part of the function right here, because you're over on the left of +2. So I take -8 and I put it in the parentheses, and what that means is I put it in for x right here. So what I have is -8 plus 9, and that's 1. So now I know that g of -8 equals 1. Okay, now I go to find g of g of 2. I go to find g of 2. And that's where the change occurs. I have to find out which x can actually equal 2. And it's this one right here. This one up here. X plus g of x is going to equal x plus 9 for all of the x's that are to the left of 2 or equal to 2. So what that means is 2 is going to get calculated here. So what I did was put 2 in the parentheses, which means put it in for x, for the x in x plus 9. I did that. 2 plus 9 is 11. So now I know that g of 2 is 11. Okay, now I'm being asked to find x of 8. 8 is over here on the right-hand side of x equals 2. So it's going to use this function to calculate it. I put 8 in g of 8, well, in g of x, I put 8 where the x is, and that means put 8 where this x is right here. That gives me 8 minus 8, which is 0. And so I see I have them written up here, but hey, what's life for? I'm going to write it again here. G of 8 equals 0. And now I've evaluated this function, g of x, for those three numbers. -8, 2, and 8. And I could have done it for more also. Could have done it for -3.25 if I had wanted to, if I just wanted to suffer a little more. That's what piecewise defined functions do. Each part of the domain has a little subfunction that's being used to calculate. Now I'm going to show this to you again in a slightly more complicated way. Here we have a function that's divided into 3 parts. And those parts occur at x equals -3 and x equals +4. So what I did was I drew longer lines through x equals -3 and x equals 4. Those lines are not really there, okay? It's just for me, to help me separate the domain into 3 parts. You can even think of it as part A, part B, and part C, if that helps you. Okay, so what we have is h of x, and for all of the x's to the left of -3, h of x is going to equal -5x minus 20. And for all of the x's between -3 and equaling -3, well, between -3 and 4, let's just say that, and x is allowed to equal -3. But for this group of x's, h of x is going to equal 4. And this will give us more of an idea of what that means. And for all of the x's to the right of x equals 4, or equaling x equals 4, we're going to have h of x equals x plus 3. So we have these subfunctions in command in different parts of the domain. The domain is always on the x-axis. So here we are. See, I think I was getting asked about this. Let me see if I can erase it. Yeah, I can. I was being asked a what if kind of question. Okay. Now, we have our three parts of the domain, negative infinity to -3, -3 to 4, and 4 to infinity. So let me make my infinity signs. Okay. Now over here on the left, we have h of x equaling -5x minus 20. And I'm being asked to evaluate h of x for x equals -8. So, okay, I put -8 in for the x in parentheses, and that's a code, a math code, to tell me to put -8 in for that x. I multiply -5 times -8, that gives me positive 40. Meanwhile, I have this minus 20 out there. So 40 minus 20 equals 20. And so I know that when x is -8, h of -8 equals 20. So I'm going to write it here, h of -8 equals 20. Now the next number we're asked for is a 1, which occurs right here. But before I do anything else, do you see how for -8 out here, I had to choose this function, which is h of x to the left of -3, because -8 is to the left of -3. So it's going to use this to calculate the answer. Any questions about my doing that? Okay, then let's move on. We're looking at the part of the domain, the x-axis, between -3 and +4. And we're being asked to find h of 1. Well, 1 occurs between -3 and +4. So I am going to take h of x equals 4, which is just y equals 4, and I'm going to put a 1 in the parentheses. Notice there's not an x out here for me to put the 1 in. So what that means is, no matter what the x's are, h of that number is going to equal 4. So my answer is 4. If I had been asked h of 0, the answer would be 4. H of 2, the answer is 4. H of 3, the answer is 4. It's kind of weird that way. H of -2, the answer would be 4. So between -3 and 4, no matter what your x is, you're going to get a 4. Why? Because that's the way the people who wrote the problem, that's the way they wrote the problem. All right, now, we're finally over here on the right side of 4, or equaling 4. And we've got x plus 3 in charge over there. H of x equals x plus 3. And we're being asked, yes? Okay, we're being asked to use 4. Okay, well, to find h of 4, but before I do that, I want to jump over to 9, because 9 is very clearly to the right of 4. which means it is undeniably h of 9 is going to be calculated with x plus 3. So h of 9 equals 9 put in for that x right there, plus 3. 9 plus 3 is 12. So I know that h of 9 is 12. Now comes what I think. Let me see if that sound was from someone in the waiting room. Ah, yes. Admitting, okay. Hi there, welcome. We're talking about piecewise defined functions. Okay, now here we are at 4, and 4 is one of the values where the change occurs. Here the change occurs at 4 between h of x equals 4 and h of x equals x plus 3. Okay, so I have to determine which of these functions is going to let me use x equals 4, and it's this one right here with the line underneath the inequality sign. So x is to the right of 4 or it equals 4. So that means when I calculate h of 4, I have to go over here and use x plus 3. So I'll put a 4 in the parentheses, which puts a 4 in for this x right there. 4 plus 3 is 7. And now I know that h of 4 equals 7. So when it comes to evaluating piecewise defined functions, this is what you have to do. To me, just to me, maybe not to you, but to me, it was always easier to draw the x-axis and then actually have vertical lines coming up from where the change values occur so that I can actually see the domain being separated into different parts. And each one of those parts or pieces, because this is called piecewise defined functions, which one of those pieces uses each of these different functions. So for instance, this part uses negative 5x minus 20. This part uses, well, y equals 4. And this part uses what really is y equals x plus 3. Remember, h of x is just y. So discussion on these two that just basically talk about evaluating functions, because next we're going to go to actually graphing. You can also write me your questions in the chat or send me an email or come to my office hours starting at 3. Let me see if that's somebody else in the waiting room. Yes, Parker. Okay. Wish that were easier to see. Okay. So I'll say for now there are no questions. So let us move on to graphing these babies. And we're going to start small and build up, which is a good way to go. We have f of x, which is really just y. F of x equals two different functions depending on where the x's are located. If the x's are to the left of positive 7, then we're using f of x equals negative 3 over 7x, 3/7 x, plus 2. And if the x's are all to the right of 7 or equaling 7, then we have f of x equals negative 1, which is really y equals negative 1, which, as you can see, looking a little bit ahead, is just a horizontal line. So I have graphed these for you just to make life a little easier. This is what y equals negative 3 over 7x plus 2 equals. This is what it looks like. But notice that x cannot equal 7 here for this function because there's no bar underneath the equal sign. So we have to make an open circle at 7. So I'm going to make that bigger, thicker maybe. And try to imagine the blue not being there. The blue is what you get when you get down here for all of the x's to the right of 7 or equaling 7. The answer is just negative 1. Y equals negative 1 if x is any of the numbers to the right of 7 or equaling 7. And here's what that looks like. When x is actually 7, the y value is negative 1. If x is 7.5, the y value is negative 1. If x is 8, the y value is negative 1. If x is 8.00285632, I just made that up, the y value is negative 1. And so on and so forth, forever and ever and ever, out to positive infinity. Meanwhile, let's not forget that negative infinity is out here. And I should have made that blue. I think I'll erase it and make it blue. Because after all, positive infinity is to the right of 7. And that's what this problem stipulates. We're dealing with graphs to the left of 7 and to the right of 7. Why 7? Because the authors of the book say so. This is their problem. Okay, so often you will see these graphed, or you'll graph them yourself. They're both straight lines. How do I graph straight lines? Well, over here, I found 2 points because that's always going to be the way you graph a straight line. You've got to have 2 points. So I had to choose 7 because 7 is where the functions change. You have to know where both functions are when x is 7, even when they can't actually equal 7. And notice that what you do then is you make an open circle. That green open circle went with this line because x could not actually equal 7. And I decided to let x equal 7, had no choice. And I found out that, okay, the 7's cancel, leaving me with negative 3 plus 2, which is negative 1. So doggone it, if that didn't occur right smack dab where the open circle is. So the open circle got filled in by this function right here. And all of these numbers to the right. So I should really color this in. All the numbers to the right of 7 are also going to give you a y equals negative 1. so that you have a horizontal line here. And let me put the arrow here because both of these lines go forever. This goes forever to the left, this goes forever to the right. Now, in talking about domain and range, because you're going to be doing this in the later problems, domain is all of the x values in the function. Now, when we put these two parts of the function together to equal f of x, we find out that the entire domain is the entire x-axis, even at 7, where you did have an open hole, but it got filled in. So even 7 is used here. So every x on the x-axis is going to be used for the domain because these x's are the x-coordinates of points on the graph. And now that this open hole is filled in, what we have is a continuous graph. There are no gaps. So your domain is actually going to be from negative infinity on the x-axis to positive infinity on the x-axis. I just thought I'd throw that in because in this graph, it's very easy to see. You're going to go to the left forever, you're going to go to the right forever, and all the points eventually get filled in. So you've got a domain of negative infinity to positive infinity. Now let's talk about the range, which exists on the y-axis. What I have for my range, I guess I'll go back to black here. Well, let's see. Your range starts here at -1. There's nothing graphed down here, so it's like a vacuum out in space. Nothing exists before -1 on the y-axis right here. And then notice you've got a completely continuous graph as long as these two parts are together. So all of the y's are going to be filled in all the way up forever and ever and ever. So, move this a little bit. No, I can't. Our range is actually going to start with a bracket because y actually equals -1. And then this is going to go up forever, and I didn't make a black straight line to compensate for my lack of ability to draw a straight line, especially sideways. Best I can. Okay, I'm going to use red for this then. You know, you have to make your compromises. And it just keeps going all the way to positive infinity on the y-axis. So this is the range. Starts at y equals -1 and goes up forever. So the range is going to be -1 to infinity. And the reason I wanted to show you that here is that when the two graphs are stuck together, you've got a continuous graph. There are no complications. Later on, you're going to see complications where there are discontinuities in the range. Mostly the domain is completely filled in, but the range has breaks in it that are not filled in by anything, just empty vacuum and space. And so we're going to also talk about how you compensate for those. But right now, here, let's do the domain. You know, that's just the x-axis. So that's the domain. And I'm going to save that before it goes away. Do you want to discuss this? Anybody? I'm glad to. While you're thinking, maybe, I am going to check and see if anybody's waiting to get in, and it appears not. Okay, we've got a function divided into two parts, that part and that part. Above this, we had a function divided into three parts. This part, and this part. And before that, we had a function divided into two parts. That part and that part. And each of these parts or pieces has control of parts of the domain. Since all you were asked to do in the first two problems is evaluate, that is, stick a number in for X, I didn't actually graph the graphs. But here is another story. So we actually graphed what the graphs look like in the different parts of the domain, the part of the domain to the left of 7 and the part of the domain to the right of 7, because here you've got y equals negative 3x plus 2, and down here all you've got is y equals 1. Negative 1. Y equals negative 1. Again, because the authors of the book said so. There's nothing terribly special about any of those numbers or expressions. Okay. Now, we definitely get more complicated. I am going to see, I don't think, if I've already flattened the annotations. Yeah, I can't. Okay, I can't erase this, so we are going to go on with this. I have a function that's separated into three parts because the domain is separated into three parts. And those points of separation are x equals 0 and x equals 3. So I am temporarily going to draw some red lines through the points of separation.
Are the points of separation always the numbers that are after the equal to or greater than signs?
Yes, they are. Yes, they are. Very good. Frankly, doing this with the red lines, it just makes it easier for me to tell that there's something going on. They're not really there, and I plan to erase them at the end. Okay, the lines that weren't there. Those are just where the separation occurs, and you can see what it looks like. Color this in. And this is an open circle. And this is an open circle. You'll see why in a minute. Or maybe you are already looking. And here's a closed circle. And so all the really interesting, scary stuff occurs on those red lines that show where the separation is. Okay. So when we're told that f of x equals 1/4 x plus 3 for x to the left of 0 or equaling 0, this is what they're saying. Here's x equals 0. This is what the line looks like, 1/4 x plus 3. This is what it looks like. And it keeps going down forever and forever and forever. And since x can actually equal 0, then since f of x is going to, or y, it's just y equals, is going to equal 3 when x is 0. I put a solid hole at y equals 3 there. That's where the end of the line is, and x is allowed to equal the x coordinate there, which means the y equals the y coordinate. They go together. So I'll have a solid hole there. Then f of x equals 4 if x is between 0 and 3. And what this is, f of x equals 4 just means y equals 4. It's the line y equals 4. And the line y equals 4 is a horizontal line. And here it is. Here's x equals 0, here's x equals 3. And we're talking about all of the x's between 0 and 3. Since there's no x over here with the 4, it's just the number 4. What that means is it doesn't matter what the x's are between 0 and 3. No matter what the x's are, the y will be 4 for all of these x's, which gives us this horizontal line right here. Except there have to be open circles because x doesn't equal 0 and x doesn't equal 3. And you can tell that because there's no bar underneath. So that means open circle. So you've got an open circle here at x equals 0 and an open circle at x equals 3. And for any of the other x's that are used in between, you're going to get a nice solid dot. And when you put all these dots close together, you get a solid line, a continuous line. And there it is right there. That's what f of x equals 4 looks like. Because f of x equals 4 is just y equals 4. And if you were to graph y equals 4 in your graphing calculator, you would get a horizontal line at 4. Okay. Now, f of x equals negative x, which is y equals negative x, when x is to the right of 3, or it equals 3. So that means from x equals 3, blue, from x equals 3, all the way to infinity, y is going to equal or f of x or h of x. F of x. F of x is going to equal negative x. And here's the graph of y equals negative x, the part that starts at x equals 3 and then goes to the right forever. So as the x's go to the right forever, the graph tilts out to the right forever, but it also tilts down at the same time. So this is the third part of this piecewise function. Piecewise defined function because it's defined in pieces. F of x, the function, is defined in pieces. We've got this piece, we've got this piece, and we've got this piece. And to graph this line, I found 2 points. One of the points has to be where the change occurs. Here, the nearest one is x equals 0. Let me just write that down. X equals 0 is right there. Right here. This is x equals 0. Okay, so goes all the way to negative infinity. So I wish I had not written that where I would normally put negative infinity, but here it is. Okay, so yes, I have to choose the point, the nearest point where the change occurs, and then one other point so that I can graph that line. So I chose -4. Okay, what have I got here? I've got 1/4 x. Well, I couldn't choose +4 because it's way out there. So a number to the left of 3 would be -4. I chose that because I wanted the 4s. Because I'm going to move out here. 1/4 times -4 plus 3 equals 1/4 times -4 over 1 plus 3. The 4s cancel, leaving the negative sign here, which is really a -1. So that's going to be -1 plus 3, which is 2. To get rid of fractions, you need to multiply by multiples of the denominator. So the denominator will either cancel out or divide up into them. And that's what I did. I could have gotten rid of 1/4 with -8 here, because 8 is a multiple of 4. Anyway, that's how I drew this line, as bad as it is. I found 2 points and then I drew a line through them. Now over here, I didn't really need to find 2 points, but I could have. I could have said, well, h of any x is going to be 4. So if I chose 1 as my other point, then h of 1 would have been 0. H of 4. H of 0 is 4, even though x can't equal 4. X can't equal 0. H of 0 would still be 4, but with an open circle. H of 1 would be 4. H of 2 would be 4. So that gives me more than enough points to draw a line. Oh, yeah. And then it's not just going to, well, it does kind of end out in space because at 3, it's not, x is not allowed to equal 3 from this side, so there's an open circle. See, it's not allowed to equal 3 back up here. Between 0 and 3, but not equaling 0 or 3. No, x equals 3 down here. The right side of x equals 3, and it gives us this graph right here. So after all this discussion, we need to find the domain and the range. So first let's find the domain. That's usually easier. The domain is all the x coordinates of all the points, and x coordinates live on the x-axis. One reason it's called the x-axis. So here's our x-axis right here. And notice that even though x cannot equal 0 here, it can equal 0 here, so x equals 0 does get used. And the same thing over here. X is not allowed to equal 0 here, but it is allowed to equal 0 here, so 3 gets used. So all of the x coordinates can be used. Therefore, the domain is just the x-axis, which is negative infinity to positive infinity. And that's what I wrote somewhere up here. Negative infinity all the way to the left, positive infinity all the way to the right. There are no, in the end, there are no open holes on the x-axis because they all get filled in. Now comes the challenge. Okay, I'm going to erase the red lines now. Okay, good. Okay, now let's get the range of this arm first. Let's see if I can erase that. Yeah, woo, woo, woo. Okay. Is there a color I haven't used? Red! I'm going to use red for the range. Okay, look at this arm. The range is all the y coordinates, and the y coordinates live on the y-axis. So the range of this arm is going to start here, and go down forever. Next, we come to this arm right here. This goes down forever in a slanted fashion, but it does go down. So its range can be drawn like this. Starts here at y equals 3. Talking about the range now. At y equals 3 and goes down forever. Notice how the range of this gobbles up the range of this. In fact, it includes it. So you have one continuous one continuous range going from, the way we would think of it would be going from +3 down to -infinity. Now, quite honestly, that's not the way the graph thinks about it. The way the graph thinks about it is -infinity to +3 with a bracket, because y actually equals 3. There's not an open, we don't have an open hole here, and we don't have an open hole here.
Why does the infinity go first?
Because for range, that's a very good question. For range, you always go from bottom to top, even though it's not the way we would normally think of it. Okay, so I would have to turn it around and say, from the bottom to the top, that's how I would write it. When we're writing things, they either go from left to right, always left to right, or always down to up.
Okay, thank you.
You're welcome. Now we get here. And there's a temptation to go sideways, but that's domain. Think in terms of y equals 4. There's an open hole here, but the minute you go to the right even a little bit, y actually equals 1. So in a way, y equals 4 is filled in. So if you were standing on the y-axis, you would be unaware of there being an open hole there, because all of these would have filled in that value where it's solid. So that means that y does equal 4 outside of this continuous stream. And there is nothing there. This is a vacuum. Like outer space, nothing. Well, when you've got nothing, but it connects to something, it's followed by something, and here you have nothing followed by something, we put a U. And then all that this is followed by is one number, 4. And we put 4 in braces. So this is actually the very strange way that you would write the range of f of x. It's like this is the main part, but there's also this one number that's hanging on. What do you think about that, gang? It takes some thinking about is what it takes. Okay.
Okay.
We're gonna, yes? Okay. Here's the last problem that we're gonna do, I think. Yeah. Then I've got a bunch of empty pages I have to delete. This is a nice, a pretty nice, clean graph. I need to put arrows on the end that mean go on forever. And I need to put arrows on the end. Oh, I did put it there. Okay. We're going to do this again. F of x equals the line 1/2 x when x is to the left of 0. The left of x equals 0. And x equals 0 is right here at the center. And f of x equals x plus 1 for x to the right of 0 or equaling 0. So this is y equals 1/2 x. And this is y equals x plus 1. And x equals 0 is your dividing line. So at x equals 0, your 1/2 x will be 1 times 0, which is 0. So you actually have an open circle around the origin of the x and y axis. And then any other point, I could have chosen -2, but I chose -4, just to show what would happen. If you put a -4 in for x, then I would have 1/2 times -4, which is 1/2 times -4 over 1. And 2 goes into 2 one time, 2 goes into 4 two times. So that'll give me 1 times -2 on top, and 1 times 1, which is 1 on the bottom. But -2 over 1 is just -2. So that told me that f of -4 is -2, and it gave me another point, and I was able to graph the line. 2 points to graph a line, a straight line. And I did the same thing here. I've got f of x equals x plus 1, which really is just y equals x plus 1. And this over here is really just y equals 1/2 x. Okay, so let me go back to blue. All right, what I did was this. I said if x equals 0, because you have to use the where the separation occurs, the point of separation. F of 0 equals 0 plus 1 equals 1. So when x is 0, y equals 1 for this line. And notice that x is actually allowed to equal 0, so you will have a closed hole. Then I used 4 over here, f of 4, and I put the 4 in for x, so I have 4 plus 1, and that gives me 5. So that gave me 2 lines, and I was able to graph the line from those. Now, once we've done that, I save. And then I start analyzing this graph in terms of domain and range. So for the domain first, this is an open hole. So it looks like you might have an open hole in the x-axis until, from the perspective of the x-axis, x equals 0 is filled in by this one. So you don't even know that's an open hole. All you see is that x equals 0 if you're standing on the x-axis. X equals 0 is filled in like every other x on the x-axis. So for the x-axis, this is a very continuous domain with no gaps at all. It cannot perceive the gaps which are in the y direction. So your domain is going to be negative infinity to positive infinity. Now for the range, yeah, I didn't put that all the way down here, which I should have, but it makes me lose the rest of the problem. So I just put an arrow pointing down, negative infinity that way. Negative infinity that way. Now the range, which is on the y-axis. Now let's get the domain first. The domain is the entire x-axis. Oh, there I go. This lets me completely forget that I seem totally incapable of drawing a straight line. Okay. So when it comes to the domain, I have that. Now the range. Let's look at the range. You have an arrow going all the way down. So all the y's one more time. There. Never mind. Okay. There's an open hole here for this arm. So you're actually going to have a parenthesis here. Then there's a gap, like a vacuum. Then you're going to have a solid hole, so y equals 1 will be solid and therefore a bracket. So this is your domain. This is a picture of the domain. And here's how I would write it. This is how I would translate it. infinity. From negative infinity to 0, but there's an open hole there, so I put a parenthesis. Then I have a gap followed by more stuff, so I put a U. And then because this is a solid hole, it means y really does equal 1. So I have a bracket and a 1, comma, followed by infinity, and always a parenthesis. So that's the story of the domain and the range. The domain lives on the x-axis. The range lives on the y-axis, and they never go anywhere else. I'm done. Let's discuss if you want to.
Okay. Just to make clear, the bracket means that it is equal to the number.
Yes, yes,
And
yes.
parentheses means it is not equal to the number.
Correct.
Okay.
You got it. Somebody else. These are kind of hard, but all I can say is this is a real application of real life. This is the way some businesses bill you and me. Okay, let me tell you about tomorrow. I felt like, yeah, quoting Shakespeare. We had to remember all this stuff in high school, and we had to memorize it, and it's never left my brain. And it's like haunting me. Okay. What we are going to do tomorrow is this. We're going to start off by reviewing solving systems by elimination. It's something you did in beginning algebra or algebra 1. Okay, and what you're doing, let me bring back your memories. You've got an equation of a line, you've got another equation of a line, and what you're trying to see is, do these two lines cross each other? Do they intersect? And what is the intersection point? We're going to start off doing that. And then for the, tomorrow is Thursday. For tomorrow and next week, part of next week, we're going to be working on something that all business majors have to know and all sciences majors have to know. And that doesn't leave much of anybody else. And that is, we're going to be working with the matrix. Or matrices, if you prefer. The plural is matrices. Yeah. A lot of stuff is solved with matrices. It's used extensively by defense departments all over the world. At the same time, it's used by charities all over the world, in particular, the international charities, well, all charities. that have to carry food and clothing and bandages and other medical supplies to people who are in natural disasters, like we're doing in Texas right now. So yeah. We are going to move into the world of what's called logistics, and that is a great job if you're looking toward having a career in the future. Logistics is used by militaries all over the world. It's used by shipping companies, by Amazon, by Alibaba, which is bigger than Amazon, and it's over in China, by shipping companies like J.B. Hunt. It's used by everybody, and it takes up so many different subjects. And there it is. There's logistics one more time. We're going to start the baby level of logistics, and some of you may actually fall in love with it. And some of you may not. But I promise you this, all it is arithmetic. And really, there's no reason elementary school kids couldn't do it. You've got multiplication, addition, and subtraction, and that's really all there is to it. Most of the time, you don't even divide a lot, but I guess I have to say divide. But I think if you liked arithmetic, you'll love this. And because you get a rest from so many X's and Y's. On the other hand, the story of it, if you can imagine missiles, interceptor missiles. Interceptor missiles could not work to protect our homeland if it weren't for matrices. So, gang, we are in for it starting tomorrow. So get all your homework done and up to date so you can start doing some real stuff. Talk to you tomorrow. Hang around if you've got questions.
Have a great day.
You too.
I have a question.
Yeah.
Hi. So I was having problems with my computer this morning, and I was like 2 minutes late. Did I miss anything within the 2 minutes?
We had just started going over piecewise defined functions.
Okay, I
You
think I
would
got
have picked it up in the second one.
Yeah.
So I think it's okay. And
Yeah,
you can
I
watch
think I got it.
the first part of the video too.
Okay.
But let me know if there are problems with it.
Okay, thank you. Bye. Have a good day.
You too. Emily, any questions?
No, ma'am.
Okay. Remember, you can always ask me, okay? You can email me, you can come to my office hours, all of that.
Yes.
Okay.
Okay, thank you.
Okay, talk to you later. Bye-bye. We're going to stop recording now. Bye. See you later.